So in this particular video, we will be discussing about significant figures and dimensions. This is dimensions of physical quantity. So first, let's have a discussion about significant figures. Now, when you do calculations, you often get the result in decimals, say 7.00896, or say suppose 7.00. Now, if you ask me the question, there are certain errors which arises when, say suppose you have taken 008, but you have not taken 0.00096. That is 0.00096 has been excluded. So there are certain errors which may arise because of this value that has been neglected. So this is what is the basis of the discussion of significant figures. Now sometimes when we do calculations, we often see that take the value up to 4 significant places. So when you talk about 4 significant places, we know that after a point, all the rest of the numbers are non-zero. Please keep in mind all the rest of the numbers should be non-zero. Now 7.1000. So all these numbers does not matter because it has no value. But now after point, if there are numbers, this is after zeros, if there are numbers, so this numbers has some value, has some values. So we often come across questions like take the value up to 4 significant digits. By this, we mean that we are taking the 4 places, that is up till here, 4 places. If they say up to 5 significant digits, you have to include 1, 2, 3, 4, 5. This is 0.00096. So this is your value. That is, according to the question, you have taken up to 5 significant places. Now, because of this, there are errors in your calculation while you add. Say suppose this was 0.0099 and this was 0.0099. Let's say. So if you take up to just 2 significant figures, say 0.00, and you're rounding off, or say you've included an extra 3, 0.009 plus 0.009. Now the answer is 810.ABC. But if you look over here, 0.0099 plus 0.0099. This is 8 and this becomes 9 and this becomes 1 and this becomes 0. So now you have 0.018. Over here what you have is 0.0198. So this is 8 and this becomes 9. This becomes 9. Even if you take this value 0.8 and 0.019, see this is 8 and this is 9. So you have an error that is 10 to the raised to the power minus 3. You have an error of this range. That is, it falls under 10 to the power minus 3. 1, 2, 3. So if you are having an accuracy, if you are trying to calculate an accuracy of minus 10 to the power minus 4 range, but you are discarding the fourth place significant number, then you will have error. And because of addition, you have this error. Similarly, errors that you have because of your significant figures while multiplying is known as errors due to multiplication of significant figures. So these are some of the things which we can understand relating to significant figures. Now let's come back to dimensions. So when you talk about dimensions, say suppose this is mass. So the basic unit is m, that is mass is m, length is L, time is T. So we have been given a basic unit, mass, length and time. Now using these dimensions, we can derive the rest of the quantities. Say suppose you are needed to find volume. So over here the mass becomes 0, length, volume. How do you find length? Say suppose this is the volume of a cube. This is the volume of a cube. So this is length L, this is length L and this is breadth. Height, length, height and breadth. So if you multiply length 3 times, you get the volume. So length cube into time 0, because there is no fundamental quantity for time. So this is how you can understand dimensions by having a look at this particular example. Similarly, what we have is, say suppose speed. We know speed equals to distance upon time. Now what is distance actually? Distance is the fundamental unit of length, which is denoted by L, and time is also fundamental unit, that is T. So the dimension will be, speed will be L T to the power minus 1, whereas m is 0. Similarly, if you want to find force is equal to mass into acceleration. Now what is acceleration? Acceleration, as I derived earlier, is change in velocity with respect to time. So it has a dimension of velocity and time t. Now what is velocity? Velocity or speed is nothing but distance upon time divided by time. So the dimensions of acceleration becomes L T to the power minus 2, and we have force equals to mass into acceleration. So m to the power 1, L to the power 1, T to the power minus 2 is the dimension of force. So in this way, by applying different techniques, you can understand what is dimensions. Say suppose we have different equations. Say for example, an example has been given to you, that is half mv square. So this is the dimension of energy, this is dimension of kinetic energy. Now energy should always be equal. What about potential energy? Potential energy was given as mgh. So by our law of conservation of energy, or by a logical point of view, energy's dimension should be equal. So let's find out whether this is true or not. Half mv square, the dimension will be mass into velocity square. We know velocity is nothing but length divided by time. So velocity square becomes your length square into time inverse square. So this is your dimension of kinetic energy, or simply say energy. Now let's do the calculations for potential energy. This is mgh. M is your mass, g is your acceleration due to gravity, and h is your height. This is also length. So this becomes ml into acceleration. Now we have a dimension of acceleration. Like I have said, the dimension of acceleration at this particular point that we have derived was L t to the power minus 2. So if I substitute ml into L t to the power minus 2, this becomes ml square into t to the power minus 2, which is the required dimension. Therefore we have LHS equals to RHS, and therefore we have proved. This is how you can apply this in your equations.